This lesson is section 4.4, but also incorporates bits of 4.1, 4.2, and 4.3. So today we're going to talk about the composition of transformations, and that's when two or more transformations are performed. So if each of the transformations is an isometry, and remember that means a rigid or congruence transformation, then the composition is one as well. So that means if you did a rotation, the first picture would be congruent to the second, and then if you then translated that new picture, that would also make a congruent picture, so the first and third pictures would be congruent as well. So for our first one, we are going to reflect the triangle over the x-axis, and then we're going to translate it -4, 2, the vector -4, 2. So what I like to do is I like to set up like a little table to organize my information. So I know that A was 5, 2, B was 9, 5, and C was 7, 8. So the first transformation is reflection over the x-axis. The rule for that is x negative y. So for these points, I'm going to keep the x and change the sign of the y. So those are my primes. Let's graph them. 5, -2, 9, -5, and 7, -8. So the second transformation has to happen to the new points now. These are now done to us. We're not going to use them at all. Now I'm going to use these points and I'm going to transform them along the vector -4, 2. So that means to here, I'm going to subtract 4, and then I'm going to add 2. I'm going to subtract 4 from 9. I'm going to add 2 to -5. I'm going to subtract 4. Ooh, hold on. I messed up on those first two. Not the numbers, but the notation. I'm going to subtract 4 from 7. I'm going to add 2 to -8. So notice on this last one, I put 2 apostrophes. So the newest point is now called the double prime because it's the prime of the prime. So now A double prime is at 1, 0. B double prime is at 5, -3. And C double prime is at 3, -6. All three of my triangles should be the same size and shape. They're just in different locations or orientations. For our next one, we're going to do something very similar. Let's see if I can move this or not. I can. So I'm going to list my original points again. So A was 5, 2. B was 9, 5. C was 7, 8. So the first transformation we're doing this time is the translation. Same exact vector as before, -4, 2. So I'm going to subtract 4 and get 1, add 2 and get 4. Subtract 4 and get 5, add 2 and get 7. Subtract 4 and get 3, add 2 and get 10. So now my first image is already very different from my first image last time. Let's see, 5, 7, and 3, 10. So now we're going to do our second transformation. So now the x-axis we know is x negative y. So my double primes, again, happen to the primes. So it's going to be 1, -4, 5, -7, and 3, -10. All right, so 5, -7, and 3, -10. If I compare these pictures here with the ones I just did in the last problem, they were the exact same starting coordinates. They were the exact same transformations. The only difference is the order that I completed them in. And you can see that they're in very different places. So what that tells me is that the order that they tell you to do the transformations in matters. Whatever one they say first, you must do first. And whatever one they say second, you can do second. So here's a try problem. You don't even have to graph it. You could just make your little table. If you'd like to give it a shot, pause. Answers are posted online. In this example, we want to describe the composition of transformations that mapped our original ABC onto A double prime, B double prime, C double prime. So this is my original ABC because it does not have any primes on it. So I'm going to label that as the first picture. This one has just primes on it, so that's my second picture, and this had the double primes on it, so that's my third picture. So labeling them helps me see the order that they happened in. So we went from 1 to 2 here. Visually, I could tell that it wasn't a translation. This is going to be very rough looking. Ooh, that was bad. But if I tried to take these lines and just shift them this way, it does not lay on top of it. And if I flipped it over, let's try to do flip, up, down, or left, right. Left, right would have, oh, that's not what I wanted to do. Left, right would have put it somewhere over here. Up, down, probably would have put it somewhere over here or over here. So it's not going to be a flip. So that tells me this is probably a rotation. This is probably a turn of some sort that's going to put this one triangle on top of the other. So my goal now is to look for which rule happened. Ooh, not what I wanted to do. Let's try deleting it this way. Here we go. So I'm going to look at the points that we had here. So I had 2, 1, and 1, -2. So I could see that the numbers switched places, right? Y and X switched. And then in the new one, the second spot became negative. So Y -X is actually the rule for 270-degree counterclockwise rotation about the origin. When you're describing a rotation, you should be giving the degree, the direction, saying that it was a rotation, and the point that it was turning around. If it's not the origin, you'll have to list what that ordered point is. Now I want to go from 2 to 3. Now 2 to 3, again, doesn't look like a shift, but this does look more like a flip to me. If I took this picture here, again, bad tracing, and I did an up-down flip, it looks like it lays on top of it that way. So now when I'm trying to figure out a reflection, I need to figure out what was exactly in the middle of those two triangles, right? I can start with reflection, but I am going to have to say over what line. So if I look at my A prime and my A double prime, they are 1, 2, 3, 4, 5, 6, 7, 8 spaces apart. So 4 spaces apart is halfway. So 1, 2, 3, 4. So here is my line of reflection. And that line is y equals 2. Right? It's a horizontal line. It passed through y is 2. So that is how I would describe this composition of transformations. This is one for you to try. I would recommend trying it. Pause if you'd like now. The answers are posted online. We have talked about congruence before. We've talked about angles being congruent. We've talked about segments being congruent. Figures can be congruent if and only if there's a rigid motion or a composition of rigid motions, right? A composition of transformations that maps one picture onto the other. So if I cannot come up with a way that we transformed one to become the other, they would not be considered congruent to each other. So here we want to identify any congruent figures in the coordinate plane and explain why they're congruent. So basically explain the transformation that got us from one to the other. The most obvious ones are these squares. So these squares looks like they shifted from one to the other. So if I made a congruence statement and I said that CBAD is congruent to, I'm going to make sure I match them up in the appropriate spots, like C should have matched with Q. Then we went over to B, so it goes over to P. Then we went down to A, so I'm going to go down to N, and then over to R. And the way I got from this to this, if we pick a pair of matching points, I went to the left 2, and down 1, 2, 3, 4, 5, 6. So the reason they're congruent is because we can describe it as a translation back 2, down 6. I'm using a translation vector. You could use function notation if you'd like. I think this is the easiest way. These look like they could be similar to each other. They look like they could be the same. And it does look that one is a flipped version of the other. So I can describe these as being congruent because they have a reflection. So I'm going to use a triangle symbol to make my congruent statement. So I'm going to say triangle FGE is congruent to, so F was at the top here, and if I'm flipping it, would match now with the bottom here. And then we went over this way, so we're going to go over this way, and then back to K. And we said it was because of a reflection. And this line here would be exactly in the middle of them, right? If I took 1, 2 spaces, one apart. So that's the x-axis. These last two triangles, both are 2 by 2, so they are congruent to each other. And there are two different ways I could actually describe this transformation. We've already done a reflection, because that would be one way. So we're going to use the rotation way to describe these. If I started here at J and I turned the picture 2 turns, right, 180 degrees, let's write that right now. Rotation 180 degrees. I could say counterclockwise, I could say clockwise, it doesn't matter about the origin. This J here is going to turn and end up at the U here. Oops, I probably should actually write the J first. And then if I went to the corner I from the U, I would go to the corner T. And then our last point was H, and our last point was S. If I had used a different transformation to describe the reason why I'm calling them congruent, this congruent statement would change, because if I did a reflection, J would have actually matched with S. And I'm saying that J matched with U. There are two more theorems or properties, whatever you want to call them, that we're going to learn that happen with compositions of transformations. And it's about congruent compositions. So if I reflect over a pair of parallel lines, so I started with this figure here, I reflected over line K to get my image, and then I reflected that image over line M to get my newest image. What I've really done from the first to the last is a translation. And however many spaces my parallel lines were apart, it's double that for how far apart my new and old pictures are. The other one is when you're reflecting over intersecting lines. So if I started with my picture here and I first reflected over line K and I got my new picture, and then I reflected that one over line M, what I've really done is create a rotation. So this AB here rotated to form this A double prime B double prime. So if the angle formed by the intersecting lines was X, the rotation is actually double that, or 2X. And it's always going to rotate about the intersection of the lines. If they name it, you could say about that point. If they don't name it, you could just describe it as the intersection of the lines. So for example 5 in the diagram, the figure is reflected in line K. The image is then reflected in line M. So I'm starting here, reflecting to K, reflecting over M. So I want to describe a single transformation that would map F to F double prime. So we just said if you reflect over intersecting lines, it is really a rotation about P. And if the angle formed by them was 70 degrees, it's really 140 degrees. It's double the 70. So the last one for you to try is just like this one. You could check your answer online, but that is it for section 4.4.